Okay, so we're doing a normal projectile thing. Now, the problem with our question is, it hits the top of a narrow wall, which is 8 meters high, 80 meters away, and 14 meters high, okay? So what it is it's, describe this, all right? So it's 8 meters away, and it's 14 meters high. So it's up here, and it's a point called 814. Okay, but there's two ways we could do this. You ever play Angry Birds? Two ways we can do this. We can go directly at it, that we're actually on our way up, or we have idea B is we go above and we fall back down again and we hit it on the way down. Is that all right? Now, we knew that because how many answers did it tell us we're going to have? 2, and that explains where you get your 2 answers from. Agreed? Okay. Now, what we're going to do is we're going to break this up into our components, okay? Oh dear, not like that. We're not. Okay, so like this. You can see that it has a. So is everybody happy with 4 root 2g? Okay. And 4 root 2g cos x, yeah? And 4 root 2g sin x. And then we're going to go through our usual motion of getting the equations. So the first one's 4 root 2g cos x. The next one is 4 root 2g sin x minus gt. Sx is 4 root 2g t cos x, because you're multiplying speed by time. No acceleration to worry about. And sy, 4 root 2g t sin x half gt squared. Yeah, perfect. Now here's the deal. Sort of 2 different ways of going about this, okay? So what we know happens is that at the same time, this one equals 8, while this one equals 14, because that happens at the same time frame. The distance is 8, at the same time it's 14. So we'll get easy marks on the board. It's technically one linear, one quadratic, isn't it? This is the linear equation, and this here is your quadratic equation. You're going, wow, this is a lot tougher than the linear quadratics I'm used to. But what we're going to do is we're going to isolate t. Everybody see t? So what I'm going to say is that t is 8 over 4 root 2g cos x. Everybody all right with that? Now what am I going to do with that t value, do you think? What am I going to target? See those t's there? I'm going to sub them in first. I'm going to square it out first. I'm going to do the dirty work over here. So that's going to be 64 over 16 2g cos squared x. 64 divided by 32. Just 2 over g cos squared x. All right. Now let's go with sy now. Okay, so we're subbing into sy, and this is difficult, all right? So 4 root 2g, and then the t. Well, that's handy because what's going to happen to the 4 root 2g's? You did. They're going to cancel, aren't they? Okay. And then minus a half gravity times what I just got here, wasn't it? That's a 2 over g cos squared x. See that sy? What can I change that into? We know it's 14, don't we? Now, this is where something that's really difficult looking and it is very difficult looking, all of a sudden will become very easy. What cancels out? And what does this become? Oh, and I have to highlight something else first. Here's our targeting. What do you think I should change that to? I asked you to take it down in the start class before we entered here. Huh? Tan, yeah. So what can we turn this whole system into? 8 tan x. You cool with that? Now, what happens to this g and this g? This 2 and this 2. What's left over? 1 over cos squared x. Did I give you anything for that as well? What did I say? 1 over cos squared x is the same as? So I'm just going to sub it in, aren't I? Just going to get rid of that. I'm going to sub it in for this. 14 equals 8 tan x. What's it? Minus 1. Minus tan squared x. Going to bring it all over one side. Anyone know how to finish this off? What type of equation is that? It's actually a quadratic. So if you were to do that, it'd be tan x minus 3 and tan x minus 5. And there's two answers. Tan x equals 3, which is the shallower throw. And tan x equals 5, which is the higher throw. So we want the angles. Yeah, you tan inverse ball down for me. So tan inverse 3. 70 to nearest degree. 71 degrees, yeah? And then the other one? Yeah, they're both actually reasonably steep, aren't they? Yeah. Okay. Any else ones for me? Find the time of flight in each case to the nearest seconds. Well, that's not too bad. We have the time of flight up here, do we? Actually, we don't. We don't have the time of flight yet. So give me a second. Can we agree that the time of flight ends when it hits the wall? It doesn't say it continues, does it? Like it skims it and continues. No, so we have to assume that the time of flight ends when you hit there. Therefore, the time of flight is that equation there. And also you guys got to do is just put in your angle into both of them. So just feed in your angle. So I'm just dragging this all the way down. It's going on a bit of a trip with me. Okay. And then I'll make 2 of them. Something nicely like that. And one of them you put in 79 and the other one you put in 71. And you compare the 2 times of flight. Which time of flight do you think should be longer? The one that went up and back down again, as opposed to the one that you threw straight at it. So what's the time of flight? Per, you do the 79 degree one. Jack, you do the 71 degree one. What? 1.38. And the other one? 2 points. 1.7.